Okay, let's continue our proof. So we started with the statement of the monotone class theorem, and then we restated this theorem as this without reference to an external Dynkin system. So now all we would like to prove is that the Dynkin system and the Sigma-Algebra generated by a common pi system are the same thing, okay? And one part is just very simple to see, because if you'd like to prove that this Dynkin system is a subcollection of the Sigma-Algebra, well, you can just say that the Sigma-Algebra is already a Dynkin system containing P, therefore it is larger than the smallest Dynkin system containing P. So that's the argument for this part. For the other part, we'd like to prove that sigma P is a subset of lambda P, the Dynkin system generated by P. And for this, we'd like to check that lambda P is a Sigma-Algebra, because if it is a Sigma-Algebra, it already contains P, so it is larger than the smallest Sigma-Algebra containing P. So now the task is reduced to proving that lambda P is a Sigma-Algebra. But lambda P is a Dynkin system. Therefore, all we have to show is that it is also a pi system. So the proof is reduced to proving that lambda P is a pi system. That's where we left off last lecture. So let's show AB in lambda P implies A intersection B is in lambda P. This doesn't look like a simple statement, and there is an original proof of this. Here's a simplification. I'm going to call it step 0. Well, you see, it's a Dynkin system. And Dynkin systems are also not very easy to deal with, just like Sigma-Algebras. The simplest one is pi system. Usually, pi systems have a special form. It's not true for Dynkin systems. But if I first show A, B in P implies A intersection B is in lambda P. So this is at least something, a starting point, right? Lambda P contains P. So let's start with this. Well, if A, B are in P, we have A intersection B is also in P, since P is a pi system. So we're done. A intersection B is in the pi system, which is a subcollection of the Dynkin system generated by this pi system. So step 0 is the starting point. Step 1. I'm not going to pass to the general case directly. What I'm going to do is to fix one set in P and play with the other one. So show A in the pi system, B in the Dynkin system generated by the pi system, implies their intersection is in the Dynkin system. I'm not passing to the full generality. Now, A is in P, B is in lambda P. Okay, that is step 1. And this is a little tricky proof. Okay, let us fix A in P and define the collection of sets for which A intersection B is in lambda P. Let's say the sets in where? In here. Well, if we can show that lambda P is a subset of P1, then we're done. Because we'd like to say that if P is coming from lambda P, then we're done. If lambda P is a subcollection of the collection of sets satisfying this property, then we're done. So I'm just using my imagination. Let's collect all subsets B for which A intersection B is in lambda P. Okay, very big collection. What do I know about B1? First, P is a subcollection of B1 by step 0. Because in step 0, we showed that if P is coming from P, then A intersection B is in lambda P. So if B is coming from P, then A intersection B is in lambda P. So this is by step 0. Okay? And we'd like to say that, oh, P is a subcollection of B1, so lambda P is a subcollection of B1. How can I say that? What should I prove about B1? If I can prove that B1 is a Dynkin system, then, hey, P is a subcollection of this Dynkin system, so the Dynkin system generated by this P is also a subcollection of my Dynkin system. So to conclude, lambda P1, lambda P is part of B1, it is sufficient to prove that B1 is a Dynkin system. And this is going to be left as an exercise. What do? You check the definition of Dynkin system. Okay? I'm not going to do it here. But if you do it, you're done with step 1. With step 1. Let's do step 2. We're not done. We're not done because now we have to show AB in lambda P implies A intersection B is in lambda P. We're going to use the same trick. Let's fix an A. In lambda P and define, now we're fixing it in lambda P because we need an A from lambda P, and define now B2. Just imagination, all sets for which A intersection B is in lambda P. And again, if we can show lambda P is a subcollection of B2, then we're done. So when proving step 1, we refer to step 0. So now it's time to use step 1 in the proof of step 2. We'd like to show that lambda P is a subcollection of B2. But can we say, I'm just cheating from the other board. First, P is a subcollection of now B2 by step 1. Why? How did I write that? P is a subcollection of B2. What does this say? What does this say? Well, if I pick my B from P, if I pick my B from the from the pi system, and A is already from the Dynkin system. So this is from the Dynkin system, this is from the pi system. It looks like the situation in step 1. One is coming from the pi system, the other is coming from the Dynkin system. Okay? Just think about this statement, okay? Now the roles of A and B changed. That might create some confusion. Here now B is coming from P, the pi system, and A is fixed in lambda P, which is the opposite of what is happening here. Well, to conclude that lambda P is a subcollection of B2, we need to, it is sufficient to show that B2 is a Dynkin system. And again, this is left as an exercise. And we're done with the proof. So that's a very beautiful and original theorem with a beautiful original proof. Okay? So it's not like a standard proof that you can just come up with in a few hours or anything like that. So it's an original proof. And please spend some time on understanding the ideas in this proof, okay? It's a nice proof. So one application of monotone class theorem is going to appear in the next homework. So for instance, we have this Borel sigma algebra on the real line generated by intervals, right? You can also define the Borel sigma algebra on the extended real line. What is the extended real line? It is from minus to plus infinity, including the infinities. So if you'd like to define a sigma algebra on this extended real line, you can define it using intervals of this form. For instance, okay? For instance, where B is a real number. And here you're working in the extended real line. Therefore, I'd like to point out here that the complement of this set, for instance, is B to plus infinity included. Okay? Because since we're in R bar. Okay? For instance, you can show that this usual Borel sigma algebra on the real line is the trace of the Borel sigma algebra on the extended real line on R. Remember the idea of trace. You are working on a large sample space, but you want to shrink everything to a smaller sample space. What you do is to take all measurable sets, all events of the original sample space, and intersect them with the smaller new sample space. And that way you get a sigma algebra. You call it the trace sigma algebra. Okay? So here are two definitions, okay? But you can show that this one on the smaller space is the trace of the one in the larger space on the smaller space. Okay? And for the proof of this, you can use this monotone class theorem. Okay? So what have we done so far? What have we done so far? We defined sample spaces and collections of interesting events. We called them sigma algebras. But apparently sigma algebras are too complicated. So we needed ways to deal with them. And today we discussed one important way of dealing with sigma algebras, okay? Which is to reduce maybe the ideas to smaller collections, simpler collections, like pi systems. So, but this is all about events, right? So what is next in our agenda? So remember, we're trying to build probabilistic models. What is next in our agenda? Sample space, events, now comes what? What measure? Probability measure, right? We are doing probabilities, so we need probabilities. So this brings us to our third section, probability and measure spaces. So far we had only a measurable space. This is a collection of outcomes. It's the sample space collection of all possible outcomes. And this is the Sigma-Algebra, which is the collection of interesting events. So the next is how to assign probabilities to events. So now we can discuss this question mathematically, because assigning numbers, assigning probabilities to events means just that we have to define a function on the set of events. And now we have a set of events, our Sigma-Algebra. So now we can talk about probabilities as functions. So define a function. We're going to denote it by script p from the Sigma-Algebra to positive numbers. Of course, they cannot exceed 1, with the following intuitive properties, so that we can call it a probability. Okay? What are intuitive properties of probabilities? What properties would you like your probabilities to satisfy? Just name one property of a probability from your undergraduate course. Between 0 and 1, right? So whatever event you're talking about, it should be between 0 and 1 for every event. What else? When is it 0? If it's the empty set, if nothing happens, so probability that nothing happens is 0. Is it the only case? Or did I write it wrong? Oh, yeah. 0, not 1. Sorry. And there is the other one, of course. Probability that something happens is 1. What else?
We have something like subadditivity.
Subadditivity. Let's first talk about additivity, okay? Let's say you have two events, okay, that cannot occur at the same time. So let's say you have two events, A and B. Cannot occur at the same time. What does that mean mathematically? two events, A and B, cannot occur at the same time. Disjoint, right? So if this is the case, then what can you say about the probability that one of A and B, so the probability that A or B happens? Just the total of the two probabilities, right? Is equal to probability of A plus probability B. That's all we need to define a probability measure. Let's make it a definition. So now I'm going to say let omega f be a measurable space, and you're going to understand that this is a non-empty set, and that's a sigma algebra on omega. Okay, let be a measurable space. Okay, a function, let me say a set function. Set function means that it's defined on a collection of sets, is called a probability measure if it satisfies the following properties. First is that the probability of the full space is 1. And second is the following. So it's again kind of a minimal definition. P is countably additive. Okay, here's the precise meaning. If A1, A2, etc. are events that are disjoint, and now you know what it means, right? Just take any two of those sets and their intersection is empty, then the probability of the union, so probability that one of those events, A1, A2, etc., is going to happen is the sum of the probabilities of the individual events. In this case, omega fp is called a probability space. And if an event A has probability 1, then we say that A occurs almost surely, or sometimes P almost surely, if you have ambiguity about the choice of your probability measure. So almost sure means with probability 1. We're going to use this term a lot, so that's why I'd like to introduce it right now. Does it mean A is the full space, sample space? So if you have an almost sure event, does that mean A equals omega? If you have an almost sure set, almost sure event, does that mean your event is exactly equal to the full space, omega? No, right? So it's only one way. Probability of something happens is 1, but probability of other things can also be 1. Okay? Okay. Well, that's the definition. And we're going to prove some of the basic properties now. And yes?
Why don't you mean the first property over here?
This one is going to be a consequence of this definition later. Okay? That's why I didn't add it. So it's a minimal definition. It's one of the minimal definitions. So we're going to prove some of the basic properties now and prove the other important properties, such as monotonicity of probabilities, sequential continuities of probabilities later, okay, next time. So right now, I'm just going to prove very basic few properties, actually just three properties. So let omega fp be a probability space. Let's do probability of empty set being 0. How can we prove it using 1 and 2? Any volunteers? So you have countable additivity, and you have property 1. So how can you prove that the probability of empty set is 0? So let's try to find A1, A2, etc., okay, that are just empty set and the full set, okay? So because I want to use this because I want to use the full set because I have this property. I want to use the empty set because I want to prove this property. So I have maybe just these two choices. This is the empty set, and then you're going to have A2, A3, dot, dot, dot equals this, or A1 is this, and then A2, A3 are all empty sets. Which one works? Which one works for number 2? That's the question. Second one. Why? What's wrong with the first one?
Because the summation of the probabilities, first we should find disjoint sets.
And these are not disjoint. Sorry, not disjoint. Whereas these are disjoint sets. Whenever you take two sets, one of them must be the empty set. So the intersection is always an empty set. Disjoint sets. So by 2, we have probability of the union of AIs is the sum of the probabilities of AIs. But the first one is probability of omega, and then we have from I2 to infinity probability of the empty set. On the other hand, the union of those is just the full set. The union of the full set and bunch of empty sets is the full set. Therefore, this is equal to 1. This is equal to 1 plus this. So we get this equality, which gives us the sum of constants is 0, and those constants are non-negative because probability maps into the positive real line. This must be 0. That's number 1, or part A. Part B. Finite additivity. Okay, P is finitely additive, meaning that if A1 to AN are in F, with N being a finite number, are disjoint sets. Let me write it in capital. Then the probability of the union is from 1 to n is sum of the probabilities. And now for the proof of this, well, we have A1 to AN. all we have to do is to pick an plus 1, an plus 2, etc. And we can just set them to the empty set. And using A, we know that the probabilities of them are 0. So by 2, probability of, let me write it this way, probability of the big union from 1 to infinity of AIs, it's the same as the probability of the union of 1 to n, because the rest are just empty sets. So now using 2, we have the sum from 1 to n, and then from n plus 1 to infinity. From n plus 1 to infinity, we just have zeros. So this part goes away, so we're done. Probability of the finite union is sum of probabilities of individuals. Is this okay? Aaron, fine? So just pick the rest empty sets. Second sum. From 1 to n, n plus 1 to infinity. This is from 1 to n, but that's the same union as from 1 to infinity. Because A1 union dot 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 an, union empty set, union empty set, union empty set is the same as A1 union dot 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 up to an. Okay? So this is an equality without the probabilities first. Okay? Maybe one last property. So for every A, probability of A complement is 1 minus probability of A. That's also a rule that you all know from your undergraduate courses, right? So there is one side of the world and the rest of the world. The probabilities of those two disjoint sides forming the whole world gives you 1. And how can we prove it? Well, let's use part B. Let's use part B. Because in part B, we have finitely many sets. So in particular, we can use just 2 sets. Just set A1 equals A and A2 equals A complement. And of course, n is equal to 2 here. Apply B. This gives us what? Probability of the union is equal to probability of A plus probability of A complement. But probability of A union A complement is just the full set, which is 1. Which is 1. Therefore, we are also done with this property. Probability of A complement is 1 minus probability of A. We're going to have more properties next time. Okay. So since we're already tired with difficult stuff, maybe we should have some simpler things to deal with. For instance, how to define probabilities on finite sets. Okay? So the big question is how to define probabilities. And the starting point, the easier starting point, is the case where omega is finite or countably infinite. And let's say the sigma algebra is the power set. okay, just for simplicity. Well, since the sigma algebra is the power set, everything is an event, right? Just take any subset, it's an event. So no worries about the properties of sigma algebras and so on. That's what makes probability space on finite or countable spaces easy. Okay? So no worries about sigma algebras and so on. So how should we define probabilities? How can you define the probability of an event? What do you need to say? What do you need to specify to define a probability measure? A function? So how do you define this function? For sure, probability is going to assign probabilities, numbers, to every event. But every event, you know, is a bunch of outcomes brought together. And there are only finitely or countably many of them in every event. And you can see every event as the union of its singleton elements as events, right? So if you tell me the probability of the event, the singleton event of omega 1, if you tell me the probability of the singleton event omega 2, and so on, we're done, because using countable additivity of probabilities, we can always add them up and get the probability of any event you want. So in both cases, every event A is a countable set and can be written as, we did it last time, or the first time, in the first meeting. Let me write it this way. Omega, where omega is in A. Which is a countable union. Which is a countable union. So by number 2, in the definition of probability, probability of A is just the sum of probabilities of those singleton events. So the message is that to specify a probability measure P, it suffices to specify the probabilities of singletons, sometimes called elementary events. Let's call them P omega, which is the probability of the singleton event omega. So here's the proposition. Let omega be countable and F is the power set. Let P omega be a non-negative number for each omega in omega such that their sum is 1. The probabilities must add up to 1. That's the only requirement. Just give me non-negative numbers adding up to 1. This defines the probability. Then probability of A defined by sum of P omegas, where omega is in A, for each A in F, defines a probability measure on omega F. Because the nature of probability measures is very suitable to deal with countably many sets, countably many things, set operations. So if you have an event in a countable set, this event is also a countable set, and you can just see it as a bunch of singletons brought together. So if you tell me the probability of every singleton, just you can sum them and get the probability of an event. Okay? So this needs a check, which is not very difficult, but it requires a lemma. A lemma. So here's a lemma. Let A and M be a positive number for every N, M in. Let me make them I and J, sorry. I and J, okay. So then the double sum AIJs is equal to double sum AIJs in the opposite order. So 1 to infinity, 1 to infinity. Now J from 1 to infinity, I from 1 to infinity. Well, let's first prove the proposition, proof of proposition using lemma, okay? Well, we need to check P is a probability measure. So probability of the full set is just sum of all P omegas, which is 1 because they are picked this way. So let A1, A2, etc. be in F disjoint sets. And let's prove countable additivity. Let's prove that P defined this way is countably additive. First, let's apply the definition, sum of P omegas, for which omega is in the union. Sum of P omegas, for which omega is in the union. Well, I can rewrite it as sum over all omegas and an additional sum, and now i's for which omega is in AI. Because AIs are disjoint, omega can belong to only one of them. Okay? If omega is in A1, it cannot be in A2, A3, etc. Okay? So this is going to be true for only one of those i's. This statement is going to hold true for only one of those i's. Well, these are both countable sums. And if I apply my lemma, I can switch the order. Now it's going to be what? It's going to be sum over all i's from 1 to infinity. Now, omegas for which omega is in AI. P omega. And this is the definition of probability of AI. This is countable additivity. Yes?
I couldn't understand the switch. How do you make a switch?
The switch is by the lemma.
No, I understand how the index changed.
From here to here? So this is a sum over all omegas, okay, which is a countable sum. So you can also index the elements of omega like 1, 2, 3, 4, and see it as an index j from 1 to infinity, okay? And here you just have I for which omega is in AI. So it's just indeed a finite union, finite sum, or just one element here appears. It's not even a summation. The thing is that we have to write it as a summation because we don't know for which I this is going to happen. So let's enumerate all i's and see it as a summation. And once you do the switch, I think you are done. So maybe we should stop at this point, and I should leave this proof of this lemma as an exercise. It's the primitive form of Fubini's theorem, which we're going to see later when we come to double integrals. So later in the course, they're going to become double integrals. And the most primitive version of that theorem is this double sum lemma. Okay? So let's stop today and see you on Friday at 8:40.